Well, thank you all for coming. It's nice to see so many of you here. My name is Rob. I'm a theoretical particle physicist, and I'm going to deduct 10 marks from your final exam, Councillor Dent, for being late. I'm a theoretical particle physicist and a university lecturer at Royal Holloway, University of London. And today we're talking about black holes. So black holes are deservedly the topic of many different science fiction books and television programs and films because they are innately fascinating objects. Now, if some of you have come to the lectures I've given about black holes before at the museum, and I think some of you I can see have, I try to take a slightly different approach every time I talk about black holes, but necessarily there are some things I will be saying that will perhaps be familiar to you. But given that we don't teach our undergraduates about black holes until the fourth year of their degree, I think I can afford to repeat myself once or twice on this subject, because it's a tricky subject. But the approach I want to take today is slightly more astrophysical. I want to talk a little bit more about the evolution of stars, which are, as we'll find out, the progenitors of black holes in their much later years after the star has finished burning fuel and producing heat via nuclear fusion. So I want to talk about them in this context, and then we'll move on to some of the bizarre properties these objects have, such as time dilation, the way they bend and warp the passage of time if you're too close to them, and the dangers that are presented by them if you are unlucky enough to get too close to a black hole, or perhaps even worse, if a black hole is to shoot through your solar system, because the difficulty is you can't often see them coming because space is black and black holes are also black. What that looks like is quite violent, and we'll see some animations of how that would look if a very large black hole was to pass too close to our sun. So to accompany the talk, I have a couple of links that I've prepared. I've actually prepared quite a few. So there's a QR code here that links to a Google Doc that has a number of different links on it, either to past lectures I've given or web pages that explain things in a bit more depth, and so on. I'll display this later, and if anyone has any trouble scanning it, you can come up at the end, or I can email it to you or something if it's easier, okay? So this won't be the last time this will pop up, but I can put it on later. So here's a breakdown of the program we're going to follow today. I want to start by talking about gravity. And knowing about gravity is central to understanding how black holes work and where they come from. Now, human understanding of gravity has evolved over many centuries. And at the moment, our most complete theory of how gravity works comes to us from Albert Einstein. So this, well, I'll say more about it later, but it's a very peculiar, very interesting theory that is totally different to the ways previously we thought about gravity. We're then going to talk a little bit about the life cycle of stars from their birth and their formation right the way through to their death. And it's the deaths of these very largest of stars that leads to the formation of black holes. After we've spoken about that, we're going to talk about black holes as they actually are in the universe, after we briefly mention the kind of theoretical origins of black holes, because one of the interesting things about black holes that I find interesting as a theoretical physicist is that they were predicted before they were observed. We expected them to be there without having actually ever seen them, which is a remarkable piece of science. That's one of the best things science can do, is make a prediction of something that has not yet been observed and then confirm that prediction with an observation. It's a remarkable thing to be able to do, and we do that with the power of mathematics. Then we're going to talk about some of the bizarre properties of black holes, including how they change the passage of time, as described by Einstein's theory of relativity, and we're going to talk about what it would look like and feel like if you were to fall into a black hole, which is particularly gruesome as a way to die, although from some perspectives it also means you live forever and never die. So we'll talk about that contradiction in observations. And then hopefully we'll have time for questions and answers. So we're booked in for an hour and a half, but I understand that an hour and a half, as I said last week, is more time than 99.9% of people can bear to hear about theoretical physics. So if anybody needs to leave at any point, I won't be offended. You can creep out the front and it's not a problem, okay? But I'll try and give a time at about an hour in where I'll invite people to scuttle off if they like, okay? Okay, so first I want to talk about gravity. Now, historically, the first mentions of gravity date back to Aristotle. So the ancient Greeks sort of thought that gravity was a property that an object has rather than a force. as is later understood by Newton and others. So gravity would be the opposite of levity. Fire would have levity, a property that means it wants to escape away from the Earth and will rise up, and something like water or earth possesses a property of gravity, meaning it yearns to be close to the Earth. Now, of course, we understand that not to be the case anymore, but that's where the origin of the word gravity actually comes from. And if we go forwards several hundred years, we arrive at a guy called Johann Kepler. So building on work of others, such as Copernicus previously, in the 1600s, Johann Kepler publishes his laws of planetary motion. So he writes 3 of these, and he publishes them in fairly quick succession. And these laws are what leads Isaac Newton to postulate his theory of gravity. So these laws are quite interesting. Some of them are a bit abstract, but the first law, which in a way is more of a definition, says that planets, as they orbit around the sun, they do so in elliptical paths. Now, of course, this is quite a remarkable thing in itself that took a long time for people to accept, that the Earth moves around the sun rather than the sun around the Earth. And I think it's very important that we don't look down on these early philosophers that believed things like that believed the Earth was orbited by the sun. Because if you look up in the sky and you see the sun setting and see the sun rising and it feels like you're stood still, as it does right now, it's a completely natural conclusion to think that we are being orbited by the sun. That's okay. It's a very difficult thing to do, to come up with a heliocentric model where the Earth orbits the sun. It's not at all obvious. But Kepler publishes this law. The planets move around in elliptical shapes, like a squashed circle. The next law he publishes is a little bit more abstract, but this is sometimes called the law of equal areas in equal times. So if you take these 4 snapshots of the Earth, for example, as it orbits the sun, and we look at January to February, and then 6 months later, June to July, what Kepler's second law says is that in a month period, as we've got here, the area that is swept out by the line joining the sun and the Earth is going to be the same. As long as the time between the snapshots you take is the same, the area that is swept out is the same. Now, that's quite an odd way of phrasing a law of physics, because that area doesn't mean anything physical. It's an abstract concept of what happens if you join the sun and the Earth and you trace that line across. But what this really comes from is the conservation of what we call angular momentum, which is just if something is spinning, it will tend to keep spinning, and if it stops spinning, it has to impart that spin onto something else. It's a conservation law. Now, the most mathematically useful is Kepler's third law. So this is really the one that was key for Newton to work out his theory of gravity. So r here is effectively the distance from the middle to the further end of the ellipse, what we call the semi-major axis. T here is the time taken for the Earth to make one complete orbit. So T here would be the year, a year as measured by that planet, for it to go around the entirety of the sun. And r here would be the distance from the center of that orbit. And what the third law, that's okay. What the third law says is that the cube of the year, the square of the year, is proportional to the cube of the distance from the center. So right now, I know this sounds pretty abstract and pretty boring, but it's the way that Newton uses this to work out something incredible about the planets and their motion and the forces between them. So there's this apocryphal story about Newton seeing an apple fall from an apple tree, or some people even say it hit him on the head, which I think is a bit of a stretch. And certainly there are biographical accounts from about the time when Newton talks about drinking a cup of tea and watching an apple fall, and then he sort of asked himself the question, well, if the apple falls, why does the moon not fall? And then he later answers this actually as the moon is falling. It's just constantly missing the Earth as it falls, and that's what we call an orbit. But really what he does to come up with his quantitative law of gravity is he takes Kepler's laws and he works out that the only possible description of the force between the Earth and the sun that will account for Kepler's third law is if the strength of that force depends on the product of the masses and is inversely proportional to the square of the distance between them. Now, don't worry if you're not mathsy, that's one of the last equations I'm going to show, but what this means is that we now have a way of describing how hard planets and stars pull on one another, which is phenomenal, and it revolutionizes our understanding of how the solar system works, how the galaxy works, and leads to all these later, much more fancy and interesting advances in cosmology. But what's really remarkable about how Newton does this is he has to invent a new branch of mathematics to deal with these curved shapes of the planets moving around the sun. When something is curved and it continually changes, prior to Newton, that's something quite difficult mathematically to handle. If something is linear, if you're going at 30 miles per hour, you move in 1 hour, you move 30 miles, the next hour you move another 30 miles, and so on and so on. But if you're constantly changing your speed in a non-linear way, it's a bit harder to calculate how far you'll travel in 1 hour. So Newton has to invent this new branch of mathematics to deal with continuous change, and this is what we call calculus. And he uses this new branch of mathematics to uncover this secret of how the stars attract planets and so on. And he does all of this stuff. He invents this field of mathematics, which is fundamental to every other branch of mathematics we have today. And then he turns 23. So it really makes you think, well, what's the point? I'm 29 as of a few days ago, and I've not invented any new branches of mathematics, but we can't all be Isaac Newton, I suppose. But yeah, he's a phenomenal guy. He's a bit of a weirdo as well. He goes kind of crazy in his later life. He starts trying to invent the philosopher's stone and starts sticking needles in his eyes to understand how light works. But other than that, he's a pretty interesting chap. So one thing you might notice, I won't go on about this too long, is that this number, this constant in front of the force of gravity, is a very tiny number. And physicists have been scratching their heads for a very long time about why this number is so small. There are a number of reasons why it perhaps should not be as small as it appears. I'm not going to talk too much about them though, because it's getting a bit too far in the weeds. But this number is quite interesting. How small it is all I'll say. So fast forward 300-ish years, and we come to Albert Einstein. So Isaac Newton's theory of gravity is very good. It works for a lot of things. It's still what we use today for lots of different calculations. It's what we use when we're calculating trajectories of spacecrafts and to launch things to the moon. It's still the law of gravity we use. But it has a number of pathologies within it. There are a number of ways that it goes wrong. And Albert Einstein notices some of these inconsistencies. And so in 1915, he publishes 4 papers every single Thursday in, I think it's November, sorry. Every Thursday in November. I don't know why he picked that, but he did. And these papers revolutionize our understanding of gravity. It's completely different to how Newton thinks of gravity. So Newton thinks of gravity as a force between objects that have mass, but Einstein introduces something different. So I talk a little bit more about this in one of the links I've given, but effectively what Einstein does is he envisions space and time as a single structure that we call space-time. So we have 3 dimensions of space. I can move left and right, up and down, forwards and backwards, and a 4th dimension of time. And that 4th dimension of time is really important because Einstein's theory of gravity doesn't work without that 4th dimension of time. And rather than thinking of gravity as a force that attracts objects with masses, he models gravity as curvature. So if you place a mass, something like a star, into this background fabric of space-time that is everywhere around us, it creates a dent in that space-time. The analogy that's often used here, which is, again, only an analogy, is if you have something like a trampoline or a sheet, and you place a bowling ball in the middle, the bowling ball is going to curve that sheet, curve that trampoline inwards. It's going to create an indent. And you can then skim something like a marble that will spin around the edge of that indent. So rather than thinking about the sun as pulling on the earth with a force, we think of the sun as creating an indent in the fabric of space-time, and the earth kind of skims around the rim of that indent that the sun creates. So he models this in a very complicated mathematical language. This is something we don't even really teach to undergraduates anymore. But essentially what it says is that curvature, so how bent your space-time is proportional to how much stuff you have, how much matter you have. John Wheeler puts this really nicely when he says space-time tells matter how to move and matter tells space-time how to curve. So this is a complicated mathematical language, but that's effectively the gist of what it's saying. Okay? So this comes to us from Einstein. Now, how do we know Einstein was right is a reasonable question. So one of the problems with Newton's theory of gravity that I mentioned, it has some issues, is that it makes, or rather, it doesn't explain a peculiarity with Mercury's orbit. So Mercury obviously orbits very close to the Sun. It's the closest planet that orbits to the Sun, and so it exists in the strongest part of the Sun's gravitational pull, the most bent, curved space-time. And what has been observed for a long time about Mercury's orbit is that this point we call the perihelion, which is where Mercury is furthest from the Sun, appears to shift every year. So it doesn't get furthest from the Sun at the same point every year. It shifts by some angle. So it kind of looks like a, what do you call it, like a spirograph sort of thing? Yeah, exactly, yeah, kind of spiraling around. And Newton's theory of gravity cannot explain that observation. And there's this fantastic quote by Richard Feynman, one of my physics heroes, which is a really beautiful quote. I won't read the whole thing, but what he effectively says is, you know, no matter how smart you are, no matter who's making the guess or what their name is, if it disagrees with experiment, it is wrong. Now, that includes observation. So we have a theory of physics from Newton, and we have an observation that that theory cannot explain. So when there's a disagreement between our theory, no matter how good the theory is, and an observation of something that really happens in the world, the observation is always top of the pile. That's what determines whether something is right or wrong. So if Newton's theory can't explain this peculiarity of Mercury's orbit, it means there's a problem with Newton's theory. So we test Einstein's theory against this backdrop. We know that Mercury's orbit shifts every year. You can see sort of here what I mean by the kind of spirograph shape. It shifts by this tiny, tiny fraction of a degree every orbit, or about 0.01 degrees every century. And we try and calculate this, we try and reproduce this with Einstein's theory of gravity, and it reproduces it almost exactly, which is really remarkable. It means that Einstein's theory can explain this thing that previously was unexplained, and to a really, really high level of precision. So this is just one of the feathers in Einstein's cap as far as his theory of gravity is concerned. Now, you sort of might think, well, if we know that Newton's theory is kind of not quite right, and we know that Einstein's theory is better, why do we still bother teaching Newton's theory of gravity to students? Why do we still use it? And really this comes down to the idea that science does not deal with absolutes of right and wrong, absolute truth. It deals with models. Einstein's theory of gravity is a more sophisticated model, and it fixes things that Newton's theory cannot fix, and it makes predictions like the existence of black holes that Newton's theory don't really make. But Newton's theory still gets a lot right. And trying to use Einstein's theory of gravity to launch a satellite into orbit on the Earth is a bit like using, you know, a sledgehammer to crack a walnut. It's just not needed. They work in different regimes. Einstein's theory is more correct, but Newton's theory is not completely incorrect. The wrongness is a kind of spectrum between the two. Ultimately, neither of them are completely true, because Einstein's theory of gravity also breaks down. And we'll talk a little bit about where it breaks down, but as a spoiler, it's in the center of a black hole. That's where Einstein's theory of gravity stops working. Okay. So now I want to talk a little bit about the life cycle of stars. As I mentioned, it's stars that form black holes. When a star dies, a very large star, if it's big enough, it might eventually form a black hole. So to understand where black holes come from, we need to understand a little bit about the forces that are at play within stars. This pointer is really weak. Okay, so stars initially are born from clouds of gas and dust that we call nebula, or nebula is a word for a certain type of gas and dust cloud. So this is a picture here of part of the Carina Nebula, which is one of my favorite nebulae. And it has within it lots of star-forming regions where gas and dust is dense enough that it can be captured by gravity and can collapse and form new stars. So stars are, in some ways, rather like phoenixes. You know, they're born from the exploded guts of their predecessors that have previously gone supernova. So a rough outline of this formation mechanism, if we have clouds of gas and dust and rocks, you have sort of a small instability somewhere where there's a slight overdensity in gas and dust at one point. This overdensity, where there's more gas and dust in one part than there is in another, leads to a stronger pull of gravity, and this causes material to fall inwards towards that point. And of course, the more falls in, the more dense and the more heavy it becomes, so the more it pulls in even more material. And we get this gravitational collapse, where material falls in, it falls in towards a common center, and once enough of it has accumulated and the pressure and temperature has grown high enough, we have a protostar forming. So this is where nuclear fusion is just sort of about to get started, which is this process that creates heat and light within stars like our sun. So this protostar is a kind of very, very young, just being born star, and they often create these jets of plasma and radiation from their poles, which are really quite beautiful, and we can see them here. So these are called Herbig-Haro. I don't know if I'm saying that right. I've never actually heard it said, only seen it written. Herbig-Haro jets. So this is, as a star is being born, this very, very hot plasma is flung outwards at both poles, and it lights up the surrounding nebula. So this is footage of a star being born from the ashes of previous stars, which is rather beautiful. So this is the start of a star's life cycle. Now, once it has passed through this phase, it enters the main sequence. Now, this picture is taken by a local Southend photographer, David, who's in the audience. He very kindly let me use this. That's his Instagram, by the way. He's got lots of other brilliant astrophotography. But the main sequence of a star's life cycle is kind of like the Middle Age. It's where 90% of the stars in the universe are at the moment. It's where most of them spend most of their lifetimes. And it's characterized by a period of stability. So here are some more pictures David has taken, by the way, who kindly let me use them. It's characterized by a period of stability, where the forces of gravity that are pulling inwards are balanced by the forces of extreme thermal pressure and radiation trying to explode the star outwards. So a star's life cycle in this stable period is essentially a battle between gravity trying to implode the star and heat trying to explode the star. So this heat is fueled by a process of nuclear fusion, which inside of the star, at least inside of a main sequence star, is mostly combining these two nuclei here, which are called deuterium nuclei, or deuterium is just a slightly heavier version of hydrogen, where essentially it has an extra neutron in its nucleus. These are squashed together and they form helium, and they release an awful lot of energy. Now, the reason they release energy is thanks to Einstein's formula E equals mc squared. So the mass of the resulting helium atom is actually smaller than the mass of the two original deuterium atoms that were squashed together. So mass is lost and it's converted into energy via E equals mc squared. So nuclear fusion, I mean, is something that humans are really keen to be able to replicate on the Earth, because if you think about what goes in is effectively hydrogen, which is the most abundant element in the universe, and it's something we can make very cleanly and very easily from water by separating the hydrogen and oxygen. And the product that comes out is helium, which is a harmless gas that if you didn't even want it, you just let it go up in the atmosphere and it eventually drifts off into space. But actually, we really want helium, and we really need it because we use it for MRIs, for anything that requires supercooled magnets like particle accelerators, and we're running out of it. It's something we don't have enough of at the moment. So we want the product, we've got lots of the thing that goes in, and it makes energy. So it's completely clean, completely reliable energy. The only problem is we can't yet replicate the scenario that causes it to happen on the Earth. Yeah, Steve?
Is deuterium the same as helium-3?
No, so helium-3 would be this atom here, but you take away one of the neutrons. So deuterium is what you'd call it hydrogen-2 in that sort of notation you're using. Does that make sense?
Yeah, sure.
Yeah? Okay. Okay, very good. So past the main sequence phase, if a star is really, really large, what you'd call a supergiant star, its life cycle takes a much more violent path than the path our own sun will take. So this picture here is called the Eta Carinae system. It's a really interesting system here, but one of these stars inside of this nebula is extremely large. It's about 30 times the mass of our sun, and the biggest one actually is about 100 times the mass of our sun. The other is 30 times. And these stars are sort of spiraling towards each other, orbiting in a binary system. And this nebula was formed, I can't remember when now, but it was formed when essentially these stars erupted. And it's not quite clear why they erupted, but buried within this nebula, there are two very, very large stars orbiting one another. And one of them, the one that is 100 times the mass of our sun, we expect will form a black hole at some point in the future. You've got to be pretty large to form a black hole, at least sort of 20, 25 times the mass of our sun. So our sun will not form a black hole. It will lead to something we call a white dwarf star. Okay? So these supergiant stars, they expand into this supergiant phase essentially when they begin to run out of things like hydrogen inside of their core. So fusing hydrogen into helium is the main mechanism our sun is currently creating energy with. And once that hydrogen has run out inside of the core will get colder because it's not producing heat by nuclear fusion. And then that reduction in the thermal pressure that is balancing the force of gravity, now gravity overtakes and gravity squashes the core down. And that squashing of the core makes the core's temperature get much, much higher, and it can suddenly begin fusing heavier elements. So not just fusing hydrogen, it can fuse helium, and later on it will fuse even heavier elements. Now this rise in temperature by the collapsed core that's now fusing something like helium into heavier elements causes the outer layers of the star to expand massively. So here I've drawn this in red, but this could be a blue supergiant as well. But what characterizes these supergiant stars is a very, very dense core that has collapsed inwards and a very, very diffuse outer layer. So these stars are enormous when they enter this supergiant phase. So they become very, very large. Now, once the core of the star has turned entirely to iron, so iron is the heaviest element that, well, you can't fuse iron nuclei together to make heavier elements within a star. The process becomes energy inefficient, meaning it actually takes more energy to force them together than is released by the process of fusion. So iron is the upper limit in what can be made within a star. So as a result, once iron has been made inside the core, fusion within the core halts, and then this pull of gravity takes over from the thermal pressure. So the core of the star begins to collapse, and this collapse of the core triggers an explosion. It's a rebound. It's an implosion of the core rebounds, and then it collides with these outer layers, and this is what flings material out into space in what we call a supernova. So a supernova is implosion of the core, expanding back out and triggering an explosion. And what is often left behind after a supernova is what we call a remnant, a dead remnant of the core. And there are different kinds of remnant cores you can have. So I mentioned our sun will form what we call a white dwarf star, which is what happens to the lower end of stars' masses. One layer up, if you have even heavier stars, but not quite heavy enough to form a black hole, these will form what we call neutron stars, which are very interesting and exotic structures as well. But the most exotic thing that can be formed is for a very, very large star, around 20 to 25 times the mass of our sun, will lead to a black hole, which I'm now 30 minutes in. This is the first time I'm saying black hole. So we'll go a little bit quicker, I hope. So now I want to talk about black holes as they actually are in the cosmos. But I have to talk a little bit of theory before we do that. So we mentioned that in 1915, Albert Einstein publishes his theory of gravity. The way this describes space and time we spoke about. Space-time is curved by the presence of matter. Now, in the same year that Einstein publishes his theory of gravity, this guy here, Carl Schwarzschild, takes Einstein's equation and he sort of pushes it to its extreme. He tries to study what happens, when matter is sort of collapsed. What does the gravity look like around collapsed matter, something like a star that's been squashed down very, very much. And he publishes this equation, which again looks very complicated. What is maybe not appreciated here, or what I didn't emphasize, is that Einstein's equations themselves are something to be solved. They are a set of equations that describe what's going on, but it's the solution to the equation that describes what's actually happening in nature. What does the gravity of a black hole look like? What does the gravity of a star look like? It's the solution that does that. And Schwarzschild is the first to solve these equations. And what's really remarkable is that he does this while he's serving in the trenches in the First World War. So it's a really kind of quite horrendous story, and he dies the following year after an infection he picked up during the war. But he has this wonderful quote that he writes in a letter to Einstein when they're discussing his work. And he says, "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas," which I think is a beautiful thing to say, take this walk in the land of your ideas. So he publishes that during the First World War. The same year, Einstein publishes his theory of gravity. Now, what his equation contains within it is the idea that matter, if collapsed, if squashed down enough, leads to something quite bizarre. It has these consequences built into it, his solution. So we've mentioned that very, very large stars are what create black holes when they die. And there's some direct evidence here of this actually happening. So this was I think it was a blue supergiant I think, is it the Fireworks Galaxy? Yeah. So this star is called, or it's called now, N6946BH1. So not a very attractive name, but essentially, astronomers were looking at it in sort of 2009 or before 2009. This is 2007. And then they looked at it in 2009 and it became immensely brighter than it appears in this picture. And then they looked at it again in 2015 and it was completely gone. So stars tend not to just disappear, so unless it was a smudge on the lens, I don't think. Something odd has gone on here. And what astronomers strongly believe has happened is that this star has turned into a black hole, not by supernova. So not every black hole is formed by a supernova. There are lots of failed supernovae, which are not quite as bright as a real full explosion of the star. This would have been much, much brighter if it was a real supernova. But essentially, this is us sort of witnessing in two pictures over the span of 8 years, star to no star. And what's gone on there in between is the star has sort of shot off some of its outer layers as a kind of mini failed supernova, and what has been left behind is this dead core that we call the black hole. So this was a very, very large star, so it fits well within the range that we expect to form a black hole. And it's interesting because we can essentially see that happen. We can see it go from a very big star to nothing there at all, emitting almost no visible light whatsoever. Yeah?
In layman's terms,
Yeah.
how many light years away is the closest black hole to Earth?
The closest one to us, I can't remember the number, but it's on a slide later. So it will crop up. It's called Gaia BH1, the closest one we know of. There are probably many more that are much closer, which is a bit of a scary thought, but it's very hard to spot them, not only because they are black and space is black, as I mentioned, but also because they're very tiny. As we'll see later, a black hole 10 times the mass of our sun is about the size of Essex. So that's an incredible density. Yeah, Steve?
I'm not sure about this illustration here, a bit confused. It looks
Yeah.
like this hole, but with a galaxy in the middle of it.
Well, so this thing here, we're going to talk about the anatomy of a black hole in a moment, but this thing around the black hole, a black hole is almost a perfect object. It's got no structure on it. It's a completely spherical, if it's not spinning, pretty much completely spherical, clean, smooth black surface is how it would appear. But stuff falls into a black hole, and in doing so, it spirals around in an orbit before collapsing inwards, and this is called an accretion disk. So this stuff you can see here kind of glowing is the in-spiraling material from the outer layers of the star that has been captured by the gravity. So that's why it looks a bit like a galaxy. You're quite right. But way, way smaller. Tiny, tiny, like the size of, smaller than the Earth, many black holes are. Okay.
So the accretion disk is also total.
Yes, yeah. I mean, it can be quite a bit. It can be quite a lot larger, but not as large as a galaxy, certainly. Yeah, but it depends. There's a lot of variety in the accretion disks. So the basic anatomy of a black hole is quite simple to describe. There are really two parts to a kind of pure black hole without stuff falling into it. There's what we call the horizon. This is the boundary between the outside space in the universe and the interior of the black hole, which, as I'm sure many of you already know, is important because once something is inside the interior of a black hole, it cannot exit the interior of the black hole. And the other thing, which we have a name for, but really we only have a name, we don't have any understanding of it, is what we call the singularity of the black hole. Now, the way this is often described is as a point of infinite density, where all of the matter that was that dead star that has collapsed has been concentrated into something smaller than an atom. But this is a bit misleading, because the laws of physics as we understand them completely break down at the singularity of a black hole. I can't tell you whether this thing is ultimately matter. It certainly originated from matter. But how to describe it in its current state, shrouded in the horizon of the black hole, I can't give you any more information. The theory of physics we need to unlock the mystery of the singularity is not yet a theory of physics we have. I'm going to talk a little bit more about it later, but that theory is something we would call quantum gravity, which again is very good. I can say there's a name for it, but just because we've made up a name for it doesn't mean we know anything more about it than that. We don't have that theory of physics. So the singularity is really mysterious. It's not something we understand very well at all. So as I mentioned, this horizon is a one-way street. Things can fall in, but once something has fallen in, nothing can fall back out. It won't be able to exit. So we mentioned briefly this accretion disk. So this is the kind of in-spiraling matter that is collected by the black hole. If things get too close to it, it falls in, but it falls in as a spiral, because it would be quite uncommon for something to have a direct trajectory right into the black hole. Most things kind of come at it at an angle, and so they get briefly caught in an orbit and spin around before entering. Now, the reason this is sort of glowing and this is so hot, and this is an actual picture, by the way, of the event horizon, of the accretion disk of a black hole, the reason it's so hot is that this stuff, as it spirals in, it picks up a huge amount of speed. And you end up with this layer of material with more layers in and more layers out, spiraling round, and they rub up against each other. And essentially, by friction, they create a huge amount of heat. And they also create lots of interesting dynamics because they produce magnetic fields, so they can produce enormous jets of plasma that fire off into space, or X-rays as well, which is how we can detect black holes. So these accretion disks have a real importance in how we know a lot of what we do about black holes. Yeah?
So, say you can go in, but you can't come out.
Yeah.
Isn't there something called Hawking radiation?
That's my last slide, yeah.
Oh, sorry.
No, that's a really good point. It's quite technical, but you're quite right. There's a way that black holes can reduce their mass. Now, you might think if a black hole can only eat and nothing can escape, it would only get bigger and bigger and never get smaller. But there is a mechanism that comes to us from Stephen Hawking that tells us how black holes can, in fact, reduce in size. Now, there are still lots of problems and lots of things we don't know about that, because one of the important features of quantum theory is this idea we call unitarity, which essentially means information is conserved. Now, in some sense, that information that goes into a black hole is either not conserved, or perhaps in another way that's even more problematic, it's cloned and is duplicated and it exists in two places at once. So there are lots of problems with Hawking radiation we don't yet know how to resolve, but we will talk about it briefly later on. That's a really good point. Are there any other questions at this point? Yeah? Oh, yeah.
So you say nothing can come out, but how do you know nothing can get out?
Well, so that's what the equations tell us, the equations that predict the existence of these things. And we've then made measurements since, the the age where we can now probe black holes in space. We can look at the things they have falling into them, and we can actually take pictures like this one of what they look like. So we now have evidence that they behave in the way we expect them to behave. But it's a really important question because a lot of this feels really abstract, and it feels almost like I could be making it up as I go along, which I promise I'm not. But a lot of it is led by what the equations tell us. But we have a lot of evidence that Einstein's equations that predict the existence of black holes are really, really strong. It's a really, really strong theory. It's really robust. Every test we've ever made of Einstein's theory of gravity pretty much has come up spot on. There are some deviations, which is where we need this new theory of quantum gravity. But every measurement we've made has been really, really robust. So we trust what the equations are saying to quite a high degree. But of course, you only have to make one measurement that contradicts those equations, and then the measurement takes the top of the pile, right? That's the thing we test truth against, not the equations. Yeah, did you have a question?
Where you say that Einstein says that space-time is curved,
Yeah,
and that's how gravity works.
yeah.
Does that mean that it's as if space-time is curved, or space and time are really actually curved?
So it's an interesting question because, of course, you then have to start thinking about, well, what is the structure of space-time? And this is not something we have a kind of reductionist theory of. Einstein treats space and time as these background structures, which in his equations, the equations tell us this is like the bending of a surface. They come from a branch of mathematics called differential geometry, which is all about surfaces and curvature of surfaces. So in some sense, to what level mathematics is reflecting the physical reality is a difficult question to answer, but we use the word curvature because it's the maths of curvature, and it gives us things we measure that are correct. So it's a really deep question, though, about what actually is the structure of space and time, and it's not something we have a convincing answer to. It's one of the things we expect, or we hope, quantum gravity will tell us. It will tell us something about the way space-time actually, sort of at a granular level, what it's actually doing. But quantum gravity is a bit like the tooth fairy in a way. I can say, well, hopefully quantum gravity will give us the answer. If I start saying that, it becomes a little bit too much like religion, where I'm just saying, quantum gravity will come down, the second coming of gravity, and they will answer all my questions I have about the universe. But it's not necessarily like that. We might just not be able to understand these things. Okay. Yeah, hi.
What's the point of this thing that goes around the black hole?
Yeah, so this we call the accretion disk. This is all the stuff that is falling into the black hole. But when stuff falls in, it's very rare that it's aligned so perfectly that it goes straight in and just passes through the horizon. What usually happens is that it comes in at an angle. So it's still getting pulled in by the black hole, but it's not going directly into it. And so as a result, it sort of spirals around, and it goes around a few times, losing energy before it falls in. So that's what all this material here is. This is the in-spiraling material that's rubbing up against each other at a very high speed, so it glows, it gets really hot. But it's just the way the black hole eats, basically. Very rarely stuff goes straight in. It usually takes a bit of a meander around first. Does that make sense? Yeah? Are there any other questions? Yeah?
Are there any parallels to the theoretical concepts that you're discussing here about black holes and the physical experiments that are being conducted in CERN in Switzerland?
I'm not an experimentalist, so yeah.
Are they exploring dark matter in CERN, or are they trying to recreate a black hole?
Well, so I remember when they first turned on the Large Hadron Collider, there was a lot of media hype and concern because people thought, there was a non-zero chance it could create a black hole that could grow and could then consume the Earth or something with a hyperbolic media report. So, to my knowledge, I don't know if we've learned anything about black holes at CERN because the energies that are being probed at the Large Hadron Collider are not high enough to be affected by this quantum theory of gravity, which is what would tell us about what's going on inside a black hole. And the black holes haven't been created at the Large Hadron Collider, fortunately. So we've never understood anything about them from that. So, yeah, I don't know if we learn anything about them from the LHC, not as far as I know.
I read it was like possible that very tiny black holes would be created that would instantly evaporate.
Yeah, so that's right. So tiny black holes, they evaporate very quickly by this Hawking radiation. I guess it depends what...
They could be created in CERN and then nobody would notice because they've gone too quickly.
Right, quite, yeah, exactly, yeah. Yeah?
I'm just wondering, I'm not sure you've said this already, but is black hole actually matter? Or is it just
Yeah.
actually black hole thing?
It's not like a solid thing. So, I mean, we only know about what is outside of the horizon. The horizon is the boundary of what we can look at, what we can study, what we can do science with for now. So that's not a physical structure. That is essentially a boundary in space that is caused by gravity any further in being so strong, light can't get out. That's why they appear black. It's because any light that happens to get within that boundary is being pulled inwards so strongly to the singularity it can't escape. So they appear dark because of that, for that reason. So it's not a physical structure. As we'll see when we talk about someone falling into a black hole, you pass through the horizon potentially quite safely. You know, you don't feel any immediate difficulty there. It's perhaps later in you feel the horrible effects of what the black hole does to your body. But when you're passing through the horizon, if it's a large black hole, you can pass through pretty smoothly. Does that make some sense? So it's not matter as such, the horizon. And the singularity is so far beyond our understanding, it's not really, I'm not comfortable describing that as matter either. Okay? Because another thing is black holes can form without any matter. They can form purely from curvature, which is something quite odd. So, yeah, did you have a question?
So is it like gases?
Oh, sorry, I meant the lady behind you. Sorry, go on, yeah. Can you say it again?
Is it like gas?
So they form indirectly from gas, because gas is definitely what forms the stars, and most black holes are formed from collapsed stars, as far as we know. So gas goes into stars, and then stars turn into black holes if they're big enough. This stuff around here is mostly gas, you're right. The accretion disk, the material that spirals in, that's what helps us actually see the black hole. Like in this picture here, taken with the Event Horizon Telescope. This is the supermassive black hole at the center of our galaxy. And that's visible because of the hot gas that's falling into it. So gas is really important about them, yeah.
Would you say a neutron star is a failed black hole?
It's a bit mean to neutron stars, but you could say that, yeah. If it was much bigger, if it was much bigger, certainly it would become a black hole, yeah.
So
There's-
but neutron stars are making from extremely compressed matter.
Yes, so they are still matter, certainly. There's a limit to how big a neutron star can be. If it gets too heavy, it can no longer be supported by the pressure of the neutrons pushing against each other, and it would collapse into a black hole.
And then we can't be safe for certain ways.
Yes, well, quite. Did you have a question as well?
Yeah, it's like the singularity, like the core of the black hole.
Kind of. And we know nothing about it. This is the really difficult thing. Because we can't get any information out of the inside of a black hole, because nothing can escape, we can't do any measurements on it, so we can't make any scientific observations. And even our equations, tell us some pretty bizarre things. They are the things that tell us about time travel and the spaghettification we're going to talk about later. Even they don't know what goes on at the center of a black hole. So it's really completely mysterious what goes on right at the singularity. That's why we need young scientists to do something more about it, because we've not made much progress in the last 50, 60 years, so we need more people to think about it. Yeah, I'll take one more and then we'll move on a bit. Yeah?
Is there a possibility of a black hole being more than occupying more than one singularity, i.e. more than one black hole being combined together?
Yeah, so black holes certainly do merge. They combine to form bigger black holes. This is actually one of the ways that we first measured black holes directly. So we observed, where they are and what they're doing, is when black holes merge, they sort of in-spiral towards each other, and in doing so, they create these ripples in space-time we call gravitational waves, and these have been detected. For the first time, they were detected in late 2015, and it won the Nobel Prize, I think, the next year or the year after. So certainly, black holes can combine. Now, when they combine, yeah, we expect somehow their singularities combine, but we don't know much about anything at all about these singularities. But as they're merging, their event horizons kind of warp together, and the black holes sort of blob into a bigger black hole. And then there's this process we call a ring down, where the black hole sort of wobbles a little bit, and then it settles back into a nice spherical shape. But what could...
Sorry.
That's okay.
Do you think it's possible that the normal speed of light could be exceeded once you get
No, not within the event horizon. So we have models that describe what goes on between the singularity and the event horizon. Einstein's theory works for that sort of interior part. It's just at the singularity it stops working. So speed of light, no, would still be respected inside. Okay? Does that make sense to answer your question a little bit? Yeah? Okay, we'll take more later, but I want to get through a little bit more. So I mentioned this thing of the singularity. We've just spoken a little bit about it. Now, the reason that black holes are so difficult to understand in one part is that the center of the black hole, it straddles this gap between the two pillars of modern physics. Quantum mechanics, which is very good for very tiny things like atoms and subatomic particles, and general relativity, which is very good at dealing with very heavy things like planets and stars and galaxies. Now, the center of a black hole, remembering that it comes from the collapse of a very large star, but is compressed down in the formation of the black hole to something extremely tiny, is both very tiny and very heavy. So reasonably, it should therefore be informed by the theory of the very tiny and the theory of the very heavy. But there's a technical problem here, which is that we don't yet know how to combine these two theories, the theory of the tiny, quantum mechanics, and the theory of the very heavy, general relativity, Einstein's theory of gravity. So to understand the singularity of the black hole, if it even can be understood, we would need to have this theory that bridges that gap, that deals with the very heavy and the very tiny. And that's what we call quantum gravity. There are a few candidate theories. You may have heard of string theory is one theory that tries to do this, but none of them have done it sufficiently well that we can learn anything from them about what goes on inside a black hole. Okay? So it's a really big problem, and like I say, this is why we need more young people to get into physics and try and solve these problems, because so far we've not made much progress. So supermassive black holes, just a quick mention on these. One of the ways that black holes are really important in astrophysics is that we think every large galaxy, as far as we know, has a supermassive black hole at its center. Smaller galaxies don't necessarily, but pretty much every large galaxy does have a black hole at its center. And these black holes can be extremely violent and interesting places. So this is an artist's illustration of what we call a quasar, which is essentially a black hole, but it's a black hole with a very, very energetic accretion disk spiraling around it. And the interaction of this accretion disk with the nearby plasma creates these jets of material. So jets of plasma and X-rays that fire out of the black hole, which is actually how we first detected black holes. So in the 70s, the first candidate we found for a black hole is called Cygnus X1, which is an X-ray source. And it's the subject of a very famous bet between Stephen Hawking and another great gravitational physicist, Kip Thorne, who took a bet that Cygnus X1, one said it wasn't a black hole, one said it was a black hole. Stephen Hawking kind of hedged his bets and said it wasn't a black hole because, you know, he would kind of win either way. If it wasn't a black hole, great, he wins a subscription to a magazine he shouldn't really have been reading. And if he didn't, then he's discovered black holes, which is great. So it's a win-win for him. So other evidence for black holes, how we've seen them, I mentioned these ripples in space-time we call gravitational waves when two black holes merge. So these were first detected in 2015 at the LIGO observatories dotted around the world. I think there's 2 in the US, 1 in Japan maybe. I might be getting that wrong. But these are huge tubes that are able to detect these tiny, tiny fractional oscillations in space-time by using laser light. And they can figure out that a gravitational wave has passed through the Earth. And we know, based on this signal, that it came from 2 very large black holes merging together and releasing a huge amount of energy in the form of these gravitational ripples, these gravitational waves. So that's one way we know black holes exist. Another way we know black holes exist more recently are the images that have been taken with the Event Horizon Telescope. So this is an image of M87, which is in the Messier 87 galaxy. This is its black hole, its supermassive black hole at the center of that galaxy. And again, what you can see here, this glowing material, is the material of the accretion disk. The horizon will be somewhere sort of buried in here in this black part. So these are direct observations of black holes. which have only really begun to be made in the last 10 years or so.
Why is it brighter on one side?
Because we're looking at it slightly from the side. So we'll look at an animation of a black hole in a minute, and you'll see the way that they bend the light around them is quite unique. So the fact we can see this at all is quite interesting, because this is actually behind the black hole. The black hole is obscuring it, but we can still see it. Okay. So as I was just mentioning, black holes have this property of bending light. So there's this fun app that I've linked up here called Black Hole Vision, which shows you what a black hole would look like if it was right in front of you with your camera. So this is a terrible selfie I took on Pier Hill with a black hole in front of me. But what you'll notice, if you look very carefully, is that obviously I'm looking at the black hole from this point of view, but you can just about see my shirt and my jumper in the rim of the black hole here, because the light from me has been bent around the black hole and has come back towards me. So black holes bend light. That's how strong their gravity is, which is quite an interesting phenomena. And we see this in the cosmos as well. So the cosmic horseshoe in the constellation of Leo, these are two galaxies, a sort of brighter orange one at the front and a blue one behind. These are very, very far apart, these galaxies, but it looks like a ring to us because the light coming from the blue galaxy in the background is being bent by the black hole within the galaxy in the foreground. So we're seeing this so-called Einstein ring of the light being bent around this black hole. So we can see these things as more observational evidence for the existence of black holes. Yeah?
When you say that the light being bent, you mean space-time in which the light is travelling?
That's very true. Yeah, I should be more clear about that. Light always travels in a straight line through space. So if your space is bent, your light, as far as it knows, is travelling in a straight line, but the actual space that it moves through, as far as we can see, is curved. So it looks like, to us, the light is taking a curved path, but as far as the light is concerned, it's travelling in a straight line. It's that the actual fabric of space that it moves through has been bent. That's what causes these interesting distortions here. Okay? So we mentioned, or one of you asked about the nearest black hole to us. So this was the number I couldn't remember. About 1,500 light years away, 1,560 light years away. So a light year, just to remind you, is how far light travels in 1 year. So light travels 300 million meters in a single second. It takes 8 minutes to come from the sun to the Earth. So the distance it travels in 1 year is a very, very large distance indeed. And this is how far light would travel in 1,560 years. So it's a pretty large distance away. But again, there probably are closer ones. We just haven't observed them yet, because black holes...
Our galaxy?
Sorry?
Is that within our galaxy?
I can't remember how big our galaxy is. It's 3 megaparsecs. So
They're very flat, though, isn't it?
yeah. So it's got to be within our galaxy. Yeah. And this black hole is about 10 times the mass of the sun. And if you were to look at its size and compare it with where we are now, so if we were sat here with the singularity at the Beecroft Gallery where we are now, the radius of this black hole would only be about 28 kilometers. So compared to how heavy they are, they're extremely tiny, which is why they have so many interesting gravitational effects. They're both very small and very heavy. So there's an enormous gravitational pull if you get too close to this black hole. This is a picture, by the way, of the Gaia BH1 system. So I think there's a star and a black hole in a binary orbit here. To give a bit more perspective, if you were to try and squash the Earth down into a black hole, to think about how dense this would be, I did a little calculation, and the calculation is, if you wanted to squash the Earth into a black hole, you'd be squashing the entire Earth into a 50p coin. That's how dense a black hole is. Imagine the whole planet. 5p coin, sorry, 5p coin. Even worse, yeah. Squashed down to a 5p coin. Okay? So they're extremely, extremely dense. Okay, so now I want to talk about some of the most interesting properties of black holes, which is their time travel properties. So we've reached the 1 hour mark, so if anyone wants to leave now, that's totally fine. You'll miss probably the most interesting bit, but that's okay. Yeah. Okay, if you do want to leave, that's fine. You can just creep out. So as I say, one of the most interesting properties of black holes is how they work as natural time machines. So this equation here comes from Karl Schwarzschild's solution to Einstein's equations. RS here stands for Schwarzschild radius. This is the distance from the center of the black hole to the edge of the event horizon. And R here is the distance from the center of the black hole to an observer, person number 1, who is measuring time by their watch. Now, the interesting thing is that the person who's very far from the black hole will experience much more time than the person who is very close to the black hole. The person far away, their clock will tick much, much more. The person closer will experience much fewer ticks on their watch. And this is not just a problem with their watches, this really is a physical effect. You know, if they had potted plants, the one who experiences more time, their plants will have grown more. If they were identical twins, the one who is further from the black hole will have aged much more than the twin who was closer to the black hole. So this is not just a problem of clocks, this is a question of the physical processes we associate with time. Yeah?
So does that mean all the clocks still tick the same, but the amount of time is actually passing?
So it's like if you were to look at your clock, wherever you were, if you were near to the black hole or far from the black hole, your watch would tick at 1 second per second, is how it would tick for you. But when these two meet up again after, if this guy is able to escape the proximity he has to the black hole, and they compare their watches, the one over here will have experienced a lot more time than the one who is closer. So if they make that comparison after, there has been a big difference in the time they've experienced. Does that make sense? Yeah? Okay. So to put this into some practice, suppose we take the Gaia BH1 black hole, which is 10 times the mass of our sun, about the size of Essex, and its edge, by the way, the radius extends roughly to the Dartford Bridge. So if you think about every time you drive to the Dartford Bridge, you're driving the radius of our nearest black hole if you come from Southend. So if we take that black hole and we get in an orbit around the black hole that extends to about central London. So we'd be 56 kilometers from the middle of the black hole, which has a radius of 28 kilometers. And we spin around it. So we get in an orbit, we go around it, we make sure we don't fall in, and we compare how much time we experience to how much time someone back on the Earth, far from the black hole, experiences. So if we spend 1 year orbiting around this black hole, which is quite a boring way to spend a year, but if you did it, and then later on you return to the Earth and you compare your watch with someone who was back on the Earth, they would have experienced 1 year and 5 months. So they would have experienced more time than you. And so when you reconvene and you talk to them, you've traveled 5 months further forwards in time than you would have traveled had you just been sat on the Earth. So this will be familiar if any of you have seen Interstellar. This is essentially what happens, right? When they spend too long around the black hole, and then when Matthew McConaughey goes back to Earth, his daughter is about 50 years older than him because she has experienced more time than he has, given that he was so close to the black hole. So this is real science. This is stuff that we know happens because the prediction that this happens is the same prediction as all of the other things that Einstein's theory of gravity predicts that we have tested. So one of those things is GPS. You couldn't possibly use GPS without Einstein's theory of gravity. The maths of this time dilation due to gravity is the same maths we use in GPS. So the reason is that the GPS satellites that are around the Earth rely on having super accurate clocks that are synchronized exactly to super accurate clocks on the Earth's surface. But the problem is that those clocks on the Earth's surface are in a stronger gravitational field than the clocks that are up in the satellites in orbit. So as a result, the ones on the satellite end up ticking at a different rate to the ones on the Earth's surface. So they have to be reset. We have to reset the clocks on the satellite. And how do we do that? We use precisely this equation that tells us how time is progressing at a different rate depending on how strong the gravity is where you are. So it's the same formula that we use to understand black holes as time machines as we do to reset our clocks to make GPS work. If you didn't do that resetting process, GPS systems would very quickly fall out of alignment and would stop being accurate. So hopefully I've convinced you that this is not complete rubbish. If you use GPS to get here, you've proved black hole time travel works, okay? So now we want to talk about the more violent side of black holes. What happens if you fall into one, or what happens if one comes too close to your star system? So what I want to show you now is an animation of what we call a tidal disruption event. So tidal comes from the same word as tides, the tides on the Earth, but tidal forces in general are a much broader kind of force. What it means is if you have something like gravity, which is stronger the closer you are to the black hole in this case, and weaker the further you are from the black hole. If something gets very near to that black hole, one end of it is being pulled with a really strong force, the end that is closest, and one end is being pulled with a less strong force. And this creates a tension, and it sort of pulls that object apart because it's dragging one side towards it stronger than it's dragging the other side towards it. And this tension can become cataclysmic, and it can cause the thing to completely rip apart. So I'm hoping this video will play, but this is what's shown when a very, very large star, this is a simulation produced by NASA and the ESA, becomes too close to a supermassive black hole. So this happens not totally infrequently at the center of galaxies when stars get too close to their central black hole. There we go. And gone. So that flash is from a sort of little mini supernova that's triggered when the star gets too close. And then we have another flash. So these are a bit rarer, but these are sometimes called hypernova, another great name by physicists, where essentially the material, as it's inspiraling towards the black hole, is compressed so much that it triggers a sudden runaway burst of nuclear fusion. And this causes essentially a little supernova around the edge of the black hole, which can be extremely violent and extremely bright. So I'll show you that maybe one more time just because it's quite cool to see. So as the star gets too close, it's ripped apart, and then you can see it spirals in and it forms this accretion disk. But now because all of this is extremely hot matter already, once it gets too dense as it's squashed around the edge of the black hole, it can ignite and flash as this hypernova, as we call it. So that could happen if a very large black hole passed through our solar system, but one that large, we'd probably see it coming. Yeah, Matt.
What is the time frame that video?
Yeah.
How long would that process take?
I think this is a timescale of months, if I remember correctly. So
Quick.
yeah, so these are things you could see happen in pretty much real time. It's not a typical astronomical timeline. Because that black hole, even though it might be very, very heavy, still might not be that large as far as cosmological scales go. You know, for example, 10 times the mass of our sun is about the size of Essex. So even if you're dealing with black holes that are 1 million times bigger than that, you're still sort of within scales that are smaller than our solar system. So things can happen quite quickly at that scale.
Have we witnessed any in reality?
I think we've seen signals of these hypernovae. I think there might be a picture later of a star going into a black hole, with some data we've taken from that. I can't remember if I included it, but yeah, we have seen evidence of this happening.
When you talk about the effect of gravity pulling things apart, it seems very much like magnetism. You know, it gets more powerful the closer you get. Yeah. It's like electrostatic forces too. Yeah, most forces tend to get stronger with distance. There are some exceptions, but yeah, electrostatic, magnetic, and gravitational all do. Okay, so that's what happens if a solar system or if a star system gets too close to a black hole. Now, what about if a person gets too close to a black hole? So here we have two people, one in blue, one in sort of orange with a red hat and a red tie. And what's going to happen is person A is going to push person B into the black hole. And we're going to look at these two people's perspectives and think about what they're going to observe. And I'm going to try and refrain from doing any impressions. So, first of all, from person A's point of view, so this is the person doing the pushing, what they see as the person approaches the black hole is person B moves more and more slowly as they move towards the horizon of the black hole. So if they were, for example, talking on a radio transmission, as person B fell in and person B was sending back a live feed of what they were experiencing to person A, person B would be saying, I'm approaching the black hole, I'm getting closer and closer. And they would slow down and slow down and slow down. And person A would never actually see person B pass through the horizon of the black hole. They would never see that happen. What would appear to happen would be person B would sort of squash against the surface, not because the surface is solid, but because as they approach the surface, the time that they experience compared to person A becomes so stretched out that for them to move a millimeter further in would take millions of years for person A looking on the outside. So they would sort of approach the horizon and sort of pancake around it eventually. And as the light coming from person B is stretched out into longer and longer wavelengths, they would become redder and redder and flatter, and until eventually they would completely obscure from view, and they would just become part of the blackness of the event horizon. So black holes are quite interesting in that you can tell what they've had for dinner by looking on the outside. Because if you get close enough and you look at what's fallen in, it's still technically plastered on the event horizon, gradually getting dimmer and redder and weaker.
Messy eaters then.
Messy eaters, very messy eaters, yeah. So that's what it looks like from person A's point of view. So that's the perspective of person A, who in some sense appears to see this person live forever or never quite fall through and never quite die. It's a horrible thought. From person B's point of view, they can pass through the horizon actually without much problem. Now, small black holes are much more dangerous than large black holes as far as what you experience when you get through the horizon. Small black holes will tend to rip you apart much more quickly in this process we call spaghettification. So this again is about these tidal forces we mentioned that ripped the star apart in the animation we saw, where the force in this case on the person's head is much, much stronger than the force on their feet. And so that pull stretches them apart and quite literally stretches them into spaghetti strands, which is where where is it? There, spaghettified, where this scientific term comes from. It's a real scientific term we use. Now, as they pass through the horizon, person B, if it's a big black hole and they're able to survive the descent towards the horizon, as they look back at the person who has pushed them in, they will see this person appear to age very, very rapidly. So person B experiences much less time than person A, who's outside of the black hole. So as they fall through, they see person A age very, very rapidly and experience much more time than they do. But it's actually worse than that. Not only do they see person A age very, very rapidly, they see stars go supernova, and they see galaxies merge, and they see all these things that take millions and billions of years of cosmic time happen in the fraction of a second as they fall through. So, well, so they would see it, but the lensing is quite intense, so they would see it as a thin slice. So you wouldn't see it necessarily very prettily, but all the light from those galaxies is kind of squashed around you. So it looks very odd. But yes, you would see this time happen very, very quickly. So you would see all this cosmological time happen in the fraction of a second. And you would sort of speed travel towards the end of the black hole's lifetime or the end of the universe, whichever comes first. So you experience a huge amount of time in a fraction of a second. So quite an interesting way to go. You get to see the end of the universe. But then once you hit the singularity, then you're definitely done for, as far as we know. And you wouldn't be able to report any of it back either, because none of your information can travel outside of the horizon. Now, that's what happens if you fall into a black hole. So that's your death by black hole. But now I want to mention the death of a black hole. So I always show this picture. This is me at 19 with Stephen Hawking and some of my university friends. So black holes, although we mentioned that they take things in and things fall into them but can't then escape, there is a mechanism that allows black holes to shrink in size. And this comes to us from Stephen Hawking. It's called Hawking radiation, and it's a very, very slow process. It takes, for a black hole the size of the sun, 1 solar mass, it would take longer than the current age of the universe for this black hole to evaporate. It's so, so slow. So we've never seen a black hole completely disappear, because there simply has not yet been enough time since black holes have existed for them to vanish. Okay? So it's a very slow process. But essentially where it comes from is the fusion of quantum mechanics with Einstein's special theory of relativity, which is his precursor to his theory of gravity. So, sorry, I'm distracted by the extremely loud music. Now, the quantum mechanics side of this is a version of Heisenberg's uncertainty principle, which we mentioned actually last week, 2 weeks ago, for those of you that were here. What this equation essentially says is that you can borrow energy from the universe as long as you don't borrow it for very long. So the vacuum of space is a kind of spontaneous fizz of particles of energy popping in and out of existence, as long as they then annihilate and disappear into nothingness very quickly. So that's the quantum mechanics side. The special relativity side is this relationship between energy and matter. If you can create energy, it means you can also create matter. The two have an equivalence. So what that tells us is that when these are combined, it births this new field we call quantum field theory, a central principle of which is that the vacuum of space is filled with this fizz of matter and antimatter spontaneously popping in and out of existence, recombining and disappearing, dissolving back into the vacuum. So this is happening all around us right now. Even the most emptiest reaches of empty space, this is happening. Okay, we know it's there because we can actually measure the consequences of this fizzing. Now, you're not breaking any rules in the long term, because you start off with nothing, you create matter and antimatter, the two then recombine and you end up back at nothing. And that's okay, because you're borrowing this matter from the universe, but you're not doing it for very long. So it is okay with quantum theory, and it's okay with special relativity, and that's good enough for me. So it works on a short time scale. You can borrow these things, and we know it happens. We've measured it. But what happens if these quantum fluctuations, as we call them, happen near the horizon of a black hole? Well, if it happens too close to the horizon, such that one of these particles, these pairs of particles fizzing in and out of existence, falls into the black hole, and one of them gets away, well, now they are separated in a way that cannot be overcome. The one that has fallen into the black hole cannot then recombine with the one that is on the outside. And so we've run into a problem. We've now got a matter particle out in the universe that has no antimatter partner, or vice versa, to annihilate with. And so we've broken Heisenberg's uncertainty principle. We borrowed matter from the universe indefinitely, not just for a very short period. So something's gone wrong. And nature knows when this has happened. Nature can't be fooled. We can't trick the universe into extracting matter from nothing long term. And so nature takes over, and the black hole correspondingly reduces in mass by the same amount of this particle that escaped, thanks to the black hole eating its partner. So this is a bit of an analogy. Okay, what's actually going on with Hawking radiation is quite technical, and it requires quite a bit of calculations. But this analogy is pretty good in that when these fluctuations happen near the horizon of the black hole, if one of those partners falls in, you're removing the possibility for the two particles to annihilate and vanish. And so nature reclaims that debt by instead reducing the mass of the black hole as compensation. Now, of course, a black hole has a mass that is many, many times the size of the sun in most cases. And what you're reducing it by here is the mass of something like a proton, which is very, very tiny. So this has to happen many, 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 many times to make any difference to the mass of the black hole, which is why this process is so very slow and takes so many tens of billions of years for a reasonable sized black hole. So we've never measured this radiation, this escaping radiation from a black hole. So this is very much a prediction. It's a theoretical insight that we have not tested experimentally or observationally. But Stephen Hawking's a pretty smart guy, so we have some faith in it. And lots of the other predictions of black holes using the same kind of methods have been tested and we know work. So this is much more theoretical. We've not yet observed this kind of radiation. So it's a theoretical way that a black hole might be able to reduce in mass. Okay? Now, yeah, questions? Does anyone have any questions? Yeah, Steve?
This minuscule mass particle
Yeah.
that escapes from the black hole, how would it escape from the black hole's gravity?
Well, so the one that
Go faster than speed light.
the one that gets away never falls in. So there are two. There's the one that falls in, and now that's gone, that's fallen in the black hole, and there's the one that doesn't fall in.
Yeah.
And the problem now is that these two cannot annihilate and vanish one another.
Yeah, I get that. So the black hole is radiating something out, but how does what it's radiating out escape from it?
Well, it's only if you're inside the horizon you can't get away. If you're on the edge like we are here, you can get away just fine. That's okay. Sorry?
Is it inside the horizon?
No, the one that gets away isn't. The one that falls in is.
Is.
Yeah.
But I was struggling to understand.
So
the
this
black
is.
hole can emit something that
Yeah. So this is why
nothing else can get out.
it's a little bit of an analogy in a way. But what I'm trying to get across here is that the universe is reclaiming the debt of the particle that should recombine to cancel to nothing.
Something like that.
And something, yes, and the black hole therefore loses a bit of mass to compensate for that. But the actual mechanism is quite a bit.
It hasn't lost it forever. It's just the life of the black hole, which is something. But
Well, it's lost that bit of mass. It just takes a really long time
the black
to.
hole's still in the universe, isn't it?
Well, until it completely evaporates, which it can do, if it's long enough. Yeah. Any other questions? Yeah.
Does the black hole shrink because the antimatter particle annihilates the matter that makes up the black hole?
So that's a really good thought. But it turns out it doesn't make a difference which particle falls in, the matter or the antimatter one. It would still reduce in mass, even if the matter one fell in. So
The antimatter that causes it to shrink in size, or is it?
it's not quite that. No, so I mean, antimatter is still has a mass to it. So it's still something falling in that would increase the mass of the black hole in normal circumstances. But it's that interplay of quantum mechanics on the edge of the black hole that means there's a debt that the black hole pays for by reducing its mass. Like I say, this in a way is a bit of an analogy. What's going on is a more complicated calculation that leads to thermal radiation being emitted from the black hole. And it's a bit more complicated, if you see what, yeah. But it would, in this analogy, whichever one fell in, the matter or the antimatter, it would still reduce. Yeah, does that make sense? Yeah, at the back there.
Is it possible for a black hole to explode?
So in a way, the hypernova we saw before is a black hole exploding, or like the edges of the black hole exploding. If a star falls in and that material gets very dense around the horizon of the black hole, it can erupt like a kind of supernova, but the black hole is still left at the end. Actually blowing up the black hole itself, I don't think that can happen. We've never seen that, we've never predicted that sort of thing would happen. They can merge, they can make new black holes, but actually breaking it apart, I think, is not something we can do. We'd have to understand more about the singularity to understand whether that could happen.
They only implode, don't they?
Yeah. Was there another question? Yeah?
So would Hawking's radiation theory work only when it's a black hole in singular, as in only one, or would that still work if you have two black holes combined?
Well, so when two black holes combine, they just make one black hole.
Yeah.
So if you had two in proximity.
That theory would still hold.
Oh yeah, absolutely, yeah. Any other questions? Yeah, Mary?
The accretion disk looks like a hula hoop going round.
Mm.
Are there hula hoops going in the other direction as well, all the way around it, or just that one?
There can be, yeah. I mean, if it's a static black hole, if it's not initially rotating, then they can be in all sorts of directions. It really depends which way it's coming in. If it's rotating, there's a tendency for it to match up with the rotation direction of the black hole itself. But you can still have things in other orbits that are not around that sort of equator. So but it's that usually when something falls in, it might be like a single big blob, like a star, and then it gets caught in that single ring orbiting around it.
Rob, you said if it's rotating, don't they all rotate then?
Practically, they do all rotate. Some rotate a lot faster than others, and some rotate slow enough that we can almost neglect it. Yeah. Yeah. Oh yeah, I will do at the end. Yeah. I'll do it now actually, just in case you want to scan it down there. Yeah. Did you have a question? Say again. Sorry.
Einstein's theory.
Mm-hmm.
Yeah, what actually is the bedsheets trampoline?
Yeah, so it's an analogy, and it's not the best analogy, but in that analogy, the bedsheet is space and time itself as a sort of structure, a single structure.
So what, you know how matter, it would kind of curve the space-time itself?
Yeah.
What would antimatter do?
Antimatter bends it in the same way. So antimatter, it has some properties that are opposite, like it has the opposite electric charge, but it still weighs the same thing. It still is mass, if that makes sense. Yeah? Okay. Yeah?
With black holes being at the centre of galaxies, does
Yeah.
that mean that the rest of the galaxies effectively its secretion disk and galaxies are eventually going to go into the black hole?
Not quite. I mean, eventually, the timescale is they will have, given hundreds of billions of years, they would all eventually spiral in. But the problem is, I think, it would take so long that by the time that happens, all of those stars that would have spiraled into the centre would already have died and perhaps formed black holes themselves. So, it's such a long process that in practice, that stuff will never end up falling in any way that we can observe or before it's already all turned into black holes or other degenerate stars like white dwarfs and neutron stars. Okay. Yeah.
How heavy would a black hole have to be for the singularity to be visible?
It's never visible. As far as we know, it's never visible. So there are theories of things called naked singularities, which are singularities without a horizon, but they're all very speculative and we've never seen them. So in black holes, as we understand them, they're always shrouded in the horizon, no matter how heavy or big it is. Does that make sense, Rory? Yeah? Okay. Yeah?
We talk a lot about the mass of black holes and stars. How do you actually calculate the mass?
Yeah, there are different ways of doing it. I mean, I think for black holes, the main way it's done is by looking at the things that orbit around them. And by looking at the shapes of those orbits, how close they are, how fast they're moving, you can figure out the mass of the black hole. You can also do it by looking at the background stars that are behind the black hole and looking at how those are bent by its presence. That's I think, how we measure the mass of supermassive black holes that have this large gravitational lensing effect that we mentioned. I showed the picture of the cosmic horseshoe. So by looking at that, you can make some inferences about the mass of the black hole. Stars, I guess it's more about looking at the planets that orbit them. That's how we measure the mass of our sun. There are lots of different tricks astronomers have for doing that. It's a good question. Yeah?
How strong is a black hole's gravity?
It depends how large the black hole is. Actually, at the horizon, I'm not sure, I don't have a number in mind. But of course, inside the horizon, it's strong enough that light can't escape. But in terms of how much you, for example, might weigh on the surface of a black hole, I don't have a good answer for that. But yeah, that's an interesting question. Yeah? Is the universe inside a black hole? So, there are some theories, yes, that the information content of our universe could be on the horizon of a black hole, because black holes are essentially the best hard drives in the universe. They're the most effective way of packing information onto a single surface. So there are these so-called holographic universe theories where our existence could be information on the event horizon of a black hole, but it's a very hard thing to measure. I mean, it's an even harder thing to get your head around, but that's a really interesting question, yeah. So the answer is maybe. Okay. So I think that's all our time. So if any of you want to leave, or if not, you can stick around at the end and ask me something. Yep, but thank you. Okay, go on, Matt. What was your question?
I'm going to return the favour of embarrassing me at the beginning and just wish you a happy belated birthday from this week.
Oh, thank you very much. Thank you.